I'm Yuqing Zhou from Toyota Research Institute of North America. Today's talk is about bio-inspired inverse design enables innovation in hydrogen fuel cell flow field plates. One slide about my organization. So Trina was founded back in 2008. We are located in Ann Arbor, Michigan. We are a research group affiliated with Toyota Manufacturing North America R&D. And we have 3 departments. This picture pretty much shows everybody in Trina. So we are a group of well under 100 researchers working on electronics, future mobility, and materials research. We are doing both fundamental core technology research as well as more product-oriented advanced development. So about fuel cell, I don't know how many of you are familiar with Toyota's ambition in hydrogen fuel cell technology. In terms of vehicles, we do have one running on the road. I believe this is probably still the only commercially available mass-produced hydrogen vehicle that you can currently buy. The development of this current second-generation vehicle started back in 1992 with several prototypes. We released the concept vehicle back in 2011 with the first gen Mirai, and Mirai in Japanese was future, I believe. So we want to use hydrogen fuel cell as the future solution. And after 7 years, we released the generation 2 in 2021, and we hope that more will come. This is about our vehicle development side. However, we also have the ambition of promoting hydrogen society, which includes a lot of technologies like used in buses, ships, heavy-duty trucks, forklift. There is some personal usage of a portable hydrogen cartridge. We're also developing highly integrated packages so that more companies can take advantages of this clean powertrain. Interestingly, in Japan, Toyota established a city under Mountain Fuji to prototype a lot of new technologies for the future. One of them was the hydrogen. So if we look deeper into what's inside of a hydrogen vehicle, we are interested in the fuel cell stack here with the zoomed in image, with a further zoomed image of showing the technology of combining oxygen with hydrogen that generate electricity and leaves water as the only byproduct, which is considered as a clean solution for the future mobility. And in this particular talk, I will be focusing on the flow field plate design, so-called the bipolar plate, which is in charge of distributing reactant and many other multiphysics functions. And this is what you're seeing as primarily a parallel type of flow field distributing different reactants in a parallel manner, which is, by the way, currently the technology of choice in the second-gen Mirai. We were challenged about 3 years ago to come up with an innovative design approach to really come up with the out-of-box ideas to design this flow field for the optimal performance. If we look at what's going on in the literature and related works, usually you're very familiar with this parallel type of flow field, maybe some serpentine type of flow field with different characteristics. Water management, which one is better to uniformly distribute reactant. This has been the choice of design method. Basically, design engineers sit down and survey different ones and select the one as the layout. And then they try to adapt this layout to the specific plate design, which is a very challenging job, right? The plate can have weird geometry. How do we adapt parallel pattern to a weird footprint geometry, for example? So it usually will go through several iterations of try and error, manual intervention, or fix things here and there, maybe further optimize the channel width for each parallel channel to have the optimal performance. And somebody even took some inspiration from nature to adopt this type of leaf-like flow field. But again, it's very difficult to adapt any of these into a real plate. On the other hand, people have been using topology optimization to design flow field in an inverse manner. That means it's objective-driven design approach that the flow field itself was automatically generated via design optimization algorithms based on the user-specified constraints and objective. So we formulate this as an optimization problem, hopefully we will get the flow field in the optimal manner as the output of the design process. However, based on what we surveyed about 3 years ago, most of these approaches applied to fluid-based approaches have been very limited to small-scale academic problems like you're seeing here, maybe a few channels, 5 to 10, which is not really scalable to what we are looking at. It's more like hundreds of channels in the real fuel cell plate. A few words about the basics of topology optimization. It was originally discovered to design elastic problems of distributing materials in the optimal manner for the given boundary condition. It has really sparked interest recently. Many companies invested in this technology. We can see some very cool designs coming out of this innovative design approach. Other similar keywords like inverse design, generative design, they're all somewhat related or rooted from the topology optimization concept. We decided to adopt an approach called homogenization method, where we transform geometric microstructures into material properties and then design the material property directly before we convert it back to structures. This from microstructure to material property was called homogenization, and from the material property that was optimized to the explicit geometry that you can fabricate was considered as dehomogenization. After the initial 1988 invention of the topologization, people actually adopted a method without homogenization. They don't like microstructure, too complicated. They just use density and material directly and then design black and white design like this. So in the past few decades, most people have adopted a density-based approach to design very complex engineering structures like airplane and bridges. Most recently, there was an interesting comeback of homogenization method enabled by modern dehomogenization techniques. As you can see, people can still design materials using the form of orientation, and then they do the dehomogenization of the explicit structure that will recover the performance you optimized so that you can fabricate the design. And these are some of these latest dehomogenization results in structures. In-house at Toyota, we spent about 3 to 4 years developing this new technology. We still use the concept of design in a homogenized manner, but dehomogenize using a very special bio-inspired pattern generation algorithm. As you can see here, I'm showing a simple example of a figure with homogenized property prescribed with some scalar field in the background. You can consider these as maybe isotropic thermal conductivity, maybe Young's modulus of the elastic problem. We can also design the underlying orientation of the material. You can consider this more like anisotropic behavior of elastic problem, maybe permeability of anisotropic porous media. During the design process, we basically determine the optimal distribution of the scalar field and the orientation field. And then during the dehomogenization process, we use a pattern generation algorithm to explicit generate geometries that will follow not only the orientation, but also the scalar field. Here you can see several dehomogenized designs ranging from discrete patterns all the way to the continuous patterns, which hopefully will recover the multiphysics performance that we originally optimized. Well, if you look at engineering applications, for those discrete patterns, it's really suited for some thermal applications of pin fins for heat sinks, acoustic panels like this. More continuous one maybe adapt to composite fiber placement, and in our specific case, fluidic problem of the bipolar plate. I want to highlight two works that we worked on in fuel cell field. This is the first work we did where we designed the flow field plate using more discrete microstructure patterns. In this particular example, this is the homogenized design where we distribute the porosity spatially. You can see some darker color here, whiter color here, representing the isotropic permeability that we were optimizing in the material form. And during the dehomogenization process, we let the patterns follow the velocity profile while obeying the underlying scalar field of either white or more grayish. So in this grayish area, we will distribute microstructures more finely so that the permeability will hopefully be smaller. And in this white region, you can see those microstructures were spaced so that we get higher permeability. And during the process, in this particular example, we have an inlet here to hopefully get uniform outlet distribution at this top edge. And we successfully achieved this relatively challenging task through prototyping and experiment. This is another work I would like to highlight. In the previous work, we were really using more discrete type of microstructures that may suffer from water management issues of water may stuck in those discrete walls so that we don't get enough current density. In this new work, we decided to use more continuous patterns so that all the channels will be nicely connected from the beginning to the end. What we do is we start with some unicell analysis. We assume the geometries of the microchannel and the gas diffusion layer underneath of it. Then we homogenize the unicell as a material, medium. In this case, anisotropic permeability was the one that we use to optimize. And during the optimization, we optimize the orientation of the anisotropic porous media in a spatially varying manner. And after several iterations of gradient-based optimization, we will get the optimal distribution of orientations. After that, we use our pattern generation algorithm to recover the orientation with explicit channel and wall designs. And on the right-hand side, you can see several different designs. Since we were using a multi-objective formulation, we can adjusting the weight of pressure drop as well as more uniform distribution of the reactant across the plate. Certain designs here are more smoothly connected with pretty much parallel type of structure, nice for pressure drop. On the other hand, we can see some more branched structures appeared, which was prioritized by the more uniform distribution of the reactant across the plate. Here is a conclusion of this work. I think these structures found was really out of box for engineers with several years of experience. They may want to design parallel or serpentine designs, but hybrid designs like this, maybe you can see some locations there are some parallel characteristic, but in other locations we will see some interdigitated characteristic as well as some serpentine characteristics. And the nice thing about this is what user provide is just the objective. And the algorithm decide where to hybridly allocate different flow field in different locations. Based on our numerical validation, this new design outperformed conventional parallel and serpentine benchmark designs, and it also shows some very interesting naturally occurring systems like lungs and leaves and blood vessels we'll see. So in summary, the hydrogen fuel cells is an extremely complex multiphysics system which requires extensive material and structure design optimization to further improve its performance. Toyota is currently in generation 2 of the first hydrogen fuel cell vehicle, and we are trying to adopt multiphysics simulation and optimization to further improve the performance of our fuel cell vehicles. In-house at our research institute, we developed a design approach that was based on homogenization-based optimization plus a bio-inspired dehomogenization to generate highly complex and intricate flow field designs. We have some other works to demonstrate the generalizability of this inverse design framework for other multiphysics problems like structural, thermal, and acoustic. In Toyota, we enjoyed using COMSOL as a rapid prototyping tool for design problems. Specifically, we use COMSOL combined with MATLAB, linked by the live link for MATLAB tool COMSOL provide for the topology and inverse design task. Inside COMSOL, we do multiphysics forward solution, automatic sensitivity analysis, and a lot of result visualization. But we also enjoy the flexibility of coding in MATLAB so that we can have our own customized optimization loop with specific optimizers, and most importantly, for topology optimization, the freedom to do the parameter continuation between different iterations. We like the nice balance of usability and customizability inside COMSOL. Most importantly, we are currently using COMSOL as the only tool to not only do the design, but also validation, right? So for the validation, we will put everything in 3D and with fine mesh. So if you're interested in some of our other multiphysics works, we use the exact same framework to design the composite structures made by tailored fiber placement. You can see this rear frame racing car example. We also use that to design innovative heat sinks with interesting fin shapes, as well as some drone structures. I would like to acknowledge our team. So this is a teamwork made not only by our US team at Trina with Dr. Didi, Dr. Lohan, Dr. Zhou, and Hiroshi Ukigawa. We also have a team in Japan, the Toyota Central R&D Labs, as well as our industry, quote unquote, industry collaborator who give us a lot of feedback about the production. With that, I have a reference list that you can read more about our recent works. Thank you.